everybody, and welcome to Echo Live. My name is Anna, and of course, I am coming to you from the Michigan Science Center's Echo Distance Learning Program. Today, we are back with even more H2OMG science experiments, all about the science of water. So we've got so many water experiments. I had way too many to show off last time that I had enough for an entirely new show today. So we're going to go through some different science tricks and riddles and things like that. Some of these you'll be able to show off to your friends and family based on what you learn here today about these different properties of water. Now I see lots of familiar faces starting to chime in the chat and in the comments of the programs that we are hosting on. If you are joining us in Facebook or on YouTube, hello. Hello to our friends who are joining in Zoom as well. If you haven't done so already, feel free to introduce yourself in the comments or the chat feature. Send me a message, tell me where you're watching from, and then we will go ahead and get started. The chat feature is your way to ask questions, to answer questions, and to make suggestions for things that you might like to see here on Echo Live or things that you might like me to try with our different experiments that I have planned today. Now, we said that we'll be showing off some different science tricks, so I figured let's just jump in with the big one. I've got a big tub of water right here in front of me on the table, and this is just water. I added just a couple drops of food coloring to the water, which makes it a little bit easier to see than if it was clear. But other than that, just water and a couple drops of food coloring, nothing else in the water whatsoever. Now, the challenge with this tub of water, you might be asking, why do I need this big tub of water? Well, I've got a piece of paper here, purple piece of paper, and the challenge in this demonstration is, do you think it's possible for me to hold this piece of paper under the water for 10 seconds without it getting wet? Tell me what you think. Do you think it's possible for me to put this piece of paper completely underwater for at least 10 seconds and have it not get wet at all? A couple people telling me in Zoom, no way, right? No way. How could I possibly hold this piece of paper underwater for 10 seconds without it getting any water on it? And I mean no drops of water at all. Lots of people telling us no, right? So you might know a little bit based on your experiment or experience with water, right? When you put things in water, they get wet. They start to absorb the water, especially things that are dry and very porous, like this piece of construction paper that I have. So you can even hear this piece of paper, it's dry. It's going to go down in the water, right? But a lot of people doubting that this is possible. Not quite sure. Lots of people, though, saying that they do believe in me. They think that I can do it. All right. Now, I've got one solution to this problem, and you guys might not like it very much, but I told you I'm going to take this piece of paper and put it under the water for 10 whole seconds. Now, what if I did this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Huh. What do you know? Totally dry, but that doesn't seem right? That doesn't exactly seem like the challenge that we were trying to address. So the people that said yes, I did accomplish it, right? But a couple of people telling me that maybe that was cheating. It didn't really utilize a lot of science, which is totally fair. So I do have another solution or another way that I'm going to attempt to submerge this entire piece of paper underwater, but keep it totally dry. Now, unfortunately, I do need another tool. So I do have another tool here, and it's just an empty glass. So just have an empty clear glass here, clear so that you can see through it. And what I'm going to do is I'm going to take my piece of paper, and I'm actually just going to crumple it up. Not super tiny, but just small enough that I can fit it inside my glass. I still want to be able to remove it so that we can check that the piece of paper is dry after our experiment. But now our piece of paper is totally inside our clear glass here. And then let's go ahead and zoom in. Let's see if we can submerge our entire device here under the water. Now, this might be something that you've tried before. Maybe you've been swimming and you've tried doing something very similar to this experiment using maybe just your hands or maybe with a cup in the bathtub before. But let's go ahead and give it a try. Remember that the challenge is 10 seconds underwater. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, that was more than 10 seconds under the water. Now let's carefully bring up our glass We're now taking the piece of paper right now. We are out of the water. I did bring a towel today since we're talking about water. And if you've been here for Echo Live in the past, you know how messy I can be. And I want to make sure we don't contaminate the results of our experience. So I'm just going to go ahead and wipe off the glass just a little bit to protect our paper inside. And let's go ahead and pull it out and let's check. Of course, my one hand that touched the glass is wet. So I'm going to dry that hand off because, again, we don't want to contaminate any of our results here. But let's go ahead. We'll open the piece of paper back up and you'll notice that it is completely dry. Our piece of paper is completely dry, even though we had submerged it under the water for 10 whole seconds. Now, how is this possible, right? This is probably something we've experienced before, but let's really dive into how this happens. When you take a glass like this one and you push it down in the water, right? We've talked about surface tension and pressure before on past episodes of Echo Live. When I take the glass and I push it down under the water, there is a barrier that's formed between the air trapped inside the glass and the water. The strong surface tension of water has something to do with this, but really it has more to do with air pressure. We've talked about the fact that there are 14.7 pounds per square inch of air pushing on every single surface here inside our atmosphere on Earth. That includes down on the water, but also from the air inside the glass onto the water. Since those forces are equal, since there's an equal amount of air pressure inside the glass as outside the glass in the air around us, right? Those forces are at balance. One doesn't push the other out of the way, which allows us to trap a big air bubble inside the glass, which allowed us to keep that piece of paper totally dry. It's all about that balance of pressure. But using this tub of water, there's another fun experiment that we can try. For this, I have a little bit of a larger glass. We can do this with either glass, and this is definitely one you should try at home. Now, the object of this activity, right, is using that same principle of air pressure. Is there a way for us to hold a glass of water upside down? Now, for this one, I don't have any mesh. We've done this experiment with Raul and on a past episode of Echo Live where we've covered a glass with some mesh lining, and we've utilized that surface tension of water to keep the water trapped inside the glass. But for this one, no mesh needed. All we're going to do is this time, we're actually going to fill the glass with water. So we've got it full all the way to the top. We're going to flip it upside down because that's the challenge. And then we're just going to slowly draw the glass out of the water. And this is why I dyed the water blue, so that you can see that now there is water above the surface of our water tank, right? There is water inside the glass as well. This again is all to do with that force of air pressure. Now, we talked about a different force earlier this week, or a different interaction with Raul. What interaction or what property in physics is trying to pull the water out of the glass and drop it down inside? Maybe if I were to pull it above the water level. What interaction or what force might we call that pulls the water down out of the glass once it's above the water? What do we call that? Think back to when Raul was here on Wednesday. What did he talk to us about? What is pulling the water out of the glass? So once I pull it above the water level, what is that force or interaction called? Not suction. Suction has something to do with what's keeping the water in the glass. Awesome job. It is gravity. Gravity, right, pulls on all things that have weight or that have mass. We have mass, which is what keeps us on the ground. Obviously, the Earth's mass is much greater than ours, which is why everything sticks to the ground instead of sticking to you or sticking to other smaller objects. But gravity really is pulling on these water molecules because they have mass too, and it wants them to be pulled down out of the glass. But you'll notice, right, that gravity is not necessarily stronger than this force of air pressure. That's something that Raul mentioned earlier this week as well, that even though gravity is one of those four main interactions of particles here on Earth, and really in the universe, that it's one of the weakest interactions, that there are many other interactions that are much, much stronger. One of them in this case is air pressure. So air pressure is pushing down on the surface of the water in the tank. And therefore, it's also pushing the water up into the glass. It wants to fill any sort of empty space that it can put the water in. It does not allow the water to push back up on it. So at this point, right, even with this tall glass, the force of gravity is much weaker than the force of air pressure, which allows the glass to pull up a ton of water. Now, there is a limit where these forces won't balance out. Now, if I had a much taller glass, right, obviously the weight of the water inside would be much greater. The greater the weight and the more mass you add, right, the less or the faster that gravity is going to win, that the water will eventually rush out or stop being pulled up from the water and go back down into the tank. But there's been lots of experiments done on that exact topic, and the distance is actually about 10 meters. That's really, really far, really, really tall. So unfortunately, it's much taller than the ceiling here in my studio. So I don't have a glass that's 10 meters tall. And so we can't actually see the limit of where gravity would beat the force of air pressure. But this is a really easy trick or a really easy experiment that you can try the next time you are out swimming in a lake or a pool or even in the bathtub. So two really easy, really fun interactions. Now, there's another way to do this experiment, which has to do with adding or taking away heat. Now, we've talked about heat and its interactions with water in the past. We know that when we add heat to atoms or molecules, especially to water, right, they start to expand, they start to take up more space because they've got so much more energy. We can manipulate that exact principle and create something very, very similar over here on this tray where I have this candle. So I have the candle, and that's going to be the source of our thermal energy or our kinetic energy, right? We said that heat is a form of evidence of kinetic energy of those moving molecules. So we're going to go ahead and I'm going to light the candle. And you'll notice that the candle is sitting in just a tray, like we said, of that water, which I dyed with just a little bit of food coloring, which is going to make it easier to see. So the food coloring is it's not a part of the reaction necessarily, but it does make it much easier to see. Now, we're going to take one of these glasses, make sure we get it nice and dry. Dry off our glass. Maybe the tall one would be more impressive for this, but we'll dry off our glass. And then we're just going to go ahead and I'm going to put the glass over the candle. Now, that's not great for candles, right? Because we know that candles work on a combustion reaction. They require fuel, heat, and oxygen in order to continue burning. But let's go ahead and set that glass down on top. And you'll notice, right, that the water is being drawn up into the glass. This is because, right, as the air inside was warmed, it started to take up more and more space. But once our candle started to go out because it ran out of oxygen inside the glass, right, that air inside the column cooled back down. Those molecules contracted, leaving behind an empty space, therefore less air pressure. So we created suction, just like Elise told me in Zoom, we created suction using that exact same principle. Because we cooled down the air and left behind empty space, the force of air pressure outside the glass was much greater than the force of air pressure inside the glass. So it pushed down on the tray of water and it filled our glass with water just a little bit, just until those molecules stopped contracting or stopped cooling. Now we're kind of balanced, right? And until all of the air or the pressure starts to equalize, our tray will actually stay just like that. So we'll just go ahead and set that off to the side. Now, what fun would it be if I didn't show you one experiment that's a little bit harder for you to try at home? Now, this is possible to recreate, but we're going to work with some different types of materials here, things you may not have at home. But if you do have these materials at home, I'm going to explain why you would need still some adult supervision for this experiment. So what I have here is a tray of ice cold water. So far we've been using room temperature water, and that's been good for all the experiments we've needed so far. But for this one, we are going to utilize this ice cold water in order to rapidly cool off some air. So this is going to be very similar to our candle experiment. But for this one, I'm actually going to take this empty glass bottle and I'm going to fill it with some boiling hot water, really, really hot water. If you were to try this at home, right, of course, boiling water can be extremely dangerous. So you, of course, need to have parental supervision or an adult that's willing to help you with this experiment. You'll notice that I'm putting on some gloves because this water is so hot. It is boiling hot, that I want to make sure we're being extra cautious and safe. And I wouldn't want to touch this bottle, right, if it had some really hot water inside. So while we get our tea kettle boiling here, it's only going to take a couple seconds because I boiled it before the program, right? Let's do a quick recap of what we've talked about so far. There are two principles coming into play here. One of them being air pressure, and the second one being that movement or that those properties of atoms and molecules when we add or take away heat. It's one of our favorite things to talk about here on Echo Live. When we add heat, like we're about to do to this bottle, molecules will expand. They'll take up more space. Thus, they'll actually build a little bit of pressure if we were to do that inside a closed container. But when we cool those molecules down, they will rapidly contract as they lose energy, therefore leaving behind an area of low pressure. So what I have here is a cap for the bottle that I've actually drilled a hole through the top and just put a little straw through the bottle. So tell me what you think. Think about what we've done so far in the experiments we've tried. If we were to take the hot air that's going to be left in this bottle and then rapidly cool it, I'm going to flip this over and stick the straw down inside my vat of cold water here. What is going to happen? Tell me what you think based on what we've talked about so far. What is the goal of this experiment? Tell me in the chat if you've got a hypothesis or an educated guess based on what we've talked about so far about these two different properties. Think about pressure, think about the movement of the atoms and molecules. Go ahead, tell me in the chat. I see some guesses starting to come in. Think about it for a second. I'm going to go ahead, now that our water has totally boiled, I'm going to go ahead and I'm going to carefully fill our glass bottle all the way to the very, very top with those really, really hot water molecules. Ooh, someone in Zoom tells me that the bottle might explode. Ooh, you might know a little bit about explosions if you've been here for a past episode of Echo Live. We said that all we need, right, is an expansion of gases in a closed container. So think about what we've got. We do have some expanding molecules, right? We've got some really, really hot things going on. We've got a bottle here full of hot water. Lots of guesses starting to come in. Awesome, you guys. All right, let's go ahead. And like we said, what we're aiming for here is the hot air left behind. Those really, really spread out, really, really energized water molecules. We'll quickly put the cap on our bottle here and then submerge the end. And would you look at that? Thank you, everyone, for being so concerned. Look at that. We almost completely filled this bottle with the cold water. You guys really thought about this really critically, right? Because when we cooled down the bottle, once we submerged it here inside our cold water, right, those molecules inside contracted. And since there's such a big difference in temperature between these, so more than just room temperature water, since there's such a large temperature difference, this is about how much empty space was left behind once those air molecules cooled. That allowed the pressure, the air pressure from the room around us to push down on the surface of the cold water, force it up, even against gravity, through the straw and filled that empty space, right? So again, that force of air pressure is much greater than the force of gravity, which allowed us to fill that bottle, even though I was holding it upside down, which is pretty cool. So if you want a close look at this, just to see kind of my experiment setup here. So like I said, I drilled a hole in the top of this bottle, and then I just put a plastic drinking straw down inside there and then hot glued it into place. You can see some hot glue here. That's important, right? Because like our friends in Zoom told us that we don't want a completely closed container here. If we had a completely closed container with a sealed lid, and we were doing a lot of this experimentation with this rapid expansion or contraction of molecules, right? that could cause some damage to our vessel, like our glass jar. But giving it this hole, right, is what makes it a little safer, and it's also what allowed the water to find an opening into the bottle, right? So the hole is important, the straw is important. Obviously, it wouldn't work if you were to just flip the bottle upside down. We want that small opening, which really gives the water that ability to rush inside. It's one of my favorite demonstrations. It's not super difficult to recreate at home. It is, but like we said, it can be a little bit dangerous since we're working with some really, really hot water here. And so, of course, make sure we're being safe. Make sure you ask questions. You can always reach out to the Michigan Science Center if you're looking for guidance on how you might recreate some experiments at home safely. Safety first, always, always, always. Now, I have another really easy, maybe a little bit safer experiment that you can try at home. All you'll need for this is 2 cups of water. 2 cups of water. And the object of this activity is actually to visualize or be able to see that rapid movement, that kinetic energy that comes from things that are really, really warm, like our warm water here. So what I'm going to do is I'm going to fill 1 beaker with hot water. So same hot water that we had used to heat our vacuum bottle there. We've got 1 beaker of hot water. And then all I need in the other one is some cold water. And I have some cold water set off to the side here. Really, really cold stuff. All right. Dry off our beaker here. That way we're able to see. And in order to be able to see the movement of these atoms and molecules, we of course just need to add something that's one of our favorite materials here to use on Echo, which is food coloring. So I have food coloring inside these 2 beakers here, or inside these 2 little dropper bottles here. And if you noticed, I was not very careful with my food coloring earlier. It is my kryptonite. I swear, no matter how many times I tell myself to be very careful with food coloring and to keep it off my hands, it just never seems to work out that way. So don't worry, I'm not bleeding. If you see red spots, it is just food coloring. Now we're going to put red food coloring in 1 beaker and blue food coloring in the other. Now, normally when we think about hot and cold, right? Maybe if you were to wash your hands, we think about red as being hot water and blue as being cold water. But if you have been around for any of our virtual planetarium programs where we've talked about stars, you might remember that in science, that's actually completely incorrect. We actually say it's the exact opposite. When we look at things that are really hot in science, things like stars or like flames, those really, really hot things are actually blue. So blue stars are very, very hot, or blue flames are very, very hot, whereas red stars or red flames are actually relatively cool. Now, no flame is cold, right? You can, of course, burn yourself on any flame. But when we talk in terms of stars and these differences between thousands and hundreds of thousands of degrees, we say that blue is hot, red is cold. So that's what we'll stick to for this demonstration here. What we're going to do is I'm just going to put the same amount of food coloring into both beakers simultaneously. So remember, blue is hot, red is cold, hot water, cold water. And I just want us to watch the movement of these molecules, right? It's a really easy experiment, but it is kind of exciting and cool. So here we go, adding our food coloring. And watch what happens. So 2 drops in each beaker. And tell me, what do you observe? It might take us a couple seconds to get full or complete results here. But tell me, is there a big difference between that movements of atoms and molecules in our cold water and our hot water? What is the difference if you see a difference? Think about in terms of speed or movement of atoms and molecules. Which one is going faster? Which is going slower? What's happening to our food coloring here? I'd love to hear your observations of this experiment because it is one that's super easy to try at home, one that I highly recommend you show your friends. Yeah, a couple people in Zoom and in Facebook. Jennifer tells us that the blue dye moved much, much faster. It's almost completely dissolved into the hot water, right? And whereas our red food coloring is still kind of working its way down. It's still kind of dropping from the surface where I added it to the water, and it's kind of slowly dispersing, but it's really just accumulating down at the bottom of the glass. Because it's a little bit denser than the water because there's dyes, obviously in this, it's water-based, but there are dyes in this. And this water is so cold that it's really not diffusing. Those molecules really aren't spreading out into the cold water. Remember, blue is hot, red is cold, just like a star. I know it might be a little bit deceiving, but I think it's really important that we talk about that point because you'll learn that later on in science if you haven't done so already. Right, but this is a really good visual representation of how those molecules move based on the different temperatures, right? In something that's very hot, right, we said that heat is evidence of kinetic energy, and we can really see that in this blue water. Since this water moves so quickly, right, the dye almost immediately diffused into the water, and now it's completely uniform, or what we might like to call a homogeneous uniform mixture. The red, still working on it, right? Still working on mixing into the water there because cold molecules don't have a lot of energy. They're moving very, very slowly, which doesn't allow the molecules inside there to really spread out. They want to stick together. They don't let things move around very fast. And so we see that right here in this really quick, really easy demonstration. So all you need, hot water, cold water, and some food coloring. And you can even do this with the exact same color. So if you only have one color food coloring at home, you can go ahead and put one drop in each, and you'll get very similar results just of the same color. But I do want to bring up a good point about what does this have to do with anything in real life, right? Okay, so what about stars? And so what about this movement of atoms and molecules in our vacuum bottle? But I'd like to point out something that my 7th grade science teacher taught me. Have you ever tried to stir something into really, really cold water? Think about stirring something like powdered lemonade or Kool-Aid powder, trying to stir that into really, really ice cold water. If you can't think about what that process was like, I recommend that you try it. What you'll notice is that you have to stir it a really long time in order to get all of those sugar molecules and the other molecules from the Kool-Aid or the lemonade powder to dissolve completely or uniformly into your cold water. Something my 7th grade science teacher taught me is that there are 2 types of people when you're making Kool-Aid. There are the people who want their lemonade right now and are willing to do a little bit of work for it. And there's the people who want to do it the easy way and are maybe a little bit more patient. What he taught us is that if you were to pour your Kool-Aid or your lemonade powder into hot water instead of cold water, you don't have to stir it at all. Just because of the kinetic energy of those water molecules, it will stir itself. It's amazing. It's a very, very cool property. I recommend you try it. But like we said, that one takes a little bit of patience because nobody wants to drink hot Kool-Aid or hot lemonade. It's just not something that we like to do. But if you can be patient and you can wait for that water to cool off, that's the easy way, right? It doesn't require any stirring. If you need your Kool-Aid right now, you can use cold water, right? Just like our red glass here, you can use cold water. But you'll have to do a lot of stirring in order to get that sugar to dissolve as it fights its way through those really, really slow moving molecules. All right, I've got one more experiment for us to try together before we head out for the day. Remember that if you have questions about anything we've tried so far, you can, of course, type them in the chat. I'm keeping an eye on that. I see lots of great hypotheses and things like that coming in. But for this, I would like to talk about one last property. And for this, I'll need you to help me make some hypotheses based on what we've learned so far here today. So in front of me, I have 2 different blocks. So let's get a close-up look at these 2 blocks. I've got 2 blocks. I want to get my water completely out of the way here. One of them is made of aluminum. We've talked about aluminum in the past, so we know aluminum is a metal. That's this one right here. This one is aluminum. You can probably hear it if I tap it with these tines. That one is aluminum. And this one, even though it looks very, very similar, this one is actually a high density foam. So it almost feels like wood. This is a high density foam, really, really dense, almost like a plastic. So this one is metal. This one is foam. Metal, foam, metal, foam. All right. Now, the object of this one is I'm going to take an ice cube and I'm going to place it on each of the blocks. One ice cube on the aluminum, one ice cube on the foam, and I want you to tell me which one is going to melt faster. So this really ties together many things we've talked about here on Echo Live in the past. But of course, I'll give you a little bit of help with this. I want to talk first about what we might know about things that are made of metal versus things that are made of plastics or other things like that. So think about if you are in your house in the winter time, or maybe even just with the air conditioning on, like we've had to do recently, if you touch something metal, and you think about how it feels, think about the temperature, right? And then you touch something metal, maybe something like your doorknob or something metal from your kitchen, which one feels colder? Does wood feel colder inside your house? Maybe you have something around you at home right now that's made of wood or of plastic. Go ahead and touch that object. And then if you have something that's made of metal near you, go ahead and touch that object. Tell me which is colder. Is it the wood or is it the metal? Wood or metal? Wood or metal? Which one is colder? Let's start with that. Yeah, right? The metal or the aluminum, that one feels colder. And we can actually prove this to you. I've got our handy dandy infrared thermometer, which is going to allow us to take a temperature reading of our two blocks here. All right, so we've got our, let's start with the aluminum one because we said that's going to be much colder. This has just been sitting here at room temperature, and that block is about 68 degrees Fahrenheit. 68 degrees Fahrenheit for our aluminum block. And then for our foam, high density foam block, we've got about 73.5 degrees Fahrenheit. So there's about a 5.5 degree difference between them. You guys are right that the metal block is much colder. So based on this information and based on your prior knowledge, which block is going to melt the ice cube faster? Now go ahead and get our ice cubes out. Tell me in the chat, tell me right now, which will melt the ice faster? Is it the cold aluminum or the warmer foam? Aluminum or foam? Aluminum or foam? Tell me in the chat. Let me get two identical ice cubes out here, or as identical as they can be. Unfortunately, the ice maker in my house is broken, and so I have no choice but to use a bag of ice, but I'll find two very similar ice cubes here. One on the foam, one on the aluminum. They are very, very similar in size. Let's go ahead and take a look. And let's see, lots of guesses starting to come in, but we are conflicted, or not, people aren't conflicted themselves, but we're getting a few different opposite responses here. We've got a couple people telling us the foam, a couple people telling us the aluminum, right? So let's go ahead and take an up close look. Our experiment is really starting to work here. And tell me, what do you notice? Remember, aluminum, foam. Aluminum, foam. The aluminum has almost entirely melted that ice cube in just the last few seconds, even though this block started off at a lower temperature. This aluminum block was much colder to start with than the foam block. And if you could see really well, let me see if I can zoom in, that foam is almost not melting the ice cube at all. Almost no melting is going on this side with our high density foam block. Whereas if we look at our aluminum, it's gone. It's just completely gone. Let's go ahead and I'm going to add another ice cube here. Maybe two this time. So we've got two more ice cubes here on our aluminum tray. We'll go ahead and let some of that water leak off the surface. Let's try that one again. All right, foam. We had a lot of people that were believing in the foam, so maybe it'll win round two here. Let's just go ahead. Now this block must be even colder, right? That block has to be even colder because it had a whole ice cube melt on top of it. Now our aluminum block, the temperature reading on our aluminum block is now about 39, 40 degrees Fahrenheit. Our foam block, just a slight drop from 68 degrees down to 66.7 degrees. So not much of a temperature change going on. This block is now almost twice the temperature of our aluminum block. We're at 35 degrees on our aluminum, 35 on the aluminum, and still about 65, 64 degrees Fahrenheit on our foam tray. So what in the world is going on? It is crazy. Just like Hong in Facebook is telling us, it's crazy, right? Maybe not what we really expected to happen. This block is very, very cold, just like all the other metal objects we touch in our houses. That one's very cold, and the foam is really, really warm. So why isn't the warm block melting the ice cube faster? This is because of a property that we call thermal conductivity. So in order for the ice to melt, it actually needs to absorb the heat from the block. So heat actually has to be transferred from the air into the block and then into the ice cube. So the block has to be able to change temperatures. And so this brings us to thermal conductivity. We've talked about conductivity in the past, which is the property of materials to allow electricity to flow through them. That's electrical conductivity, but it's very similar to thermal conductivity. That is the property of a material to be able to let heat or kinetic energy travel through it. The thermal conductivity of aluminum is much, much higher than the thermal conductivity of the foam. This aluminum is able to transfer much more heat from the air, or I can speed up the process if I were to touch these blocks with my hand. In just a couple seconds, the heat from my hand is now being transferred so quickly through the aluminum block that we will melt almost the entire ice cube. Let's go ahead and let the water out. Leave our ice cubes behind, but dump that extra water. But we can really, really easily melt that aluminum ice cube because now it's allowing the rapid transfer of the heat from my hands. Ooh, so this process is happening, right? And now the aluminum block has melted almost 3 ice cubes in the time it's taken our foam block to melt not even maybe halfway through the first ice cube here. This is thermal conductivity. And I have one more thing to show you because all elements and all materials have a different level of thermal conductivity. Just like in electricity, certain materials and certain metals are better conductors than others. Different materials, like metals, have different thermal conductivities as well. This is something important that scientists actually need to measure, which is why I have this little device right here. So this device has some temperature gauges or thermometers on it. So if we take an up close look, you can see that it is labeled. And there are 4 different types of metal bars here. And each one has a thermometer, a color changing thermometer attached to it. That is going to tell us how much of the energy is being transferred through the metal at a given point. So the 4 metals we have to test are steel, brass, aluminum, and copper. Steel and brass, these are alloys, so not metals we would find on the periodic table, but a combination of metals. And aluminum and copper are both pure metals, which we would find on the periodic table. Now, all we need to do for this is take our beaker of warm water, which we had used for our food coloring experiment. And I'm just going to go ahead and I'm going to set the ends of the bars, not the thermometers, but the ends of the bars down inside that hot water. And I want us to pay close attention to our temperature reading. Take just a moment for it to get started. And once we start to see results, I'll take it out of the water here. But the thermometers are starting to change color. Now, it's important that we don't actually drop the thermometer down in the water. So let me try to carefully zoom in without dunking it too deep here. And we are starting to see a color change, but it's just below the glass. So we're going to have to wait just a few more moments for it to get tall enough for us to see those results. Go ahead. If we want this to work more quickly, all we would need was some hotter water. Now, there's definitely a color change starting to take place. So let it go for just another second here, and then let's take an up close look all together. Let me zoom all the way in this time. And I want us to look at the color change on these thermometers. Hoping we'll be able to see it. I think it's my green screen. Let me go ahead and, as always, go ahead and turn that off. And look at the change in our thermometers, right? Starting from the ends, right? That's where the source of the heat was. The copper was able to transfer the most energy. You can see that now we've got this green color that's traveled all the way up our thermometer, all the way to the top. But in the same amount of time, the aluminum has traveled about this far. Brass is the 3rd best thermal conductor, and it's got about 3 bars filled. And then the steel, it's still just working on it. It's got maybe the first kind of 1.5, kind of barely starting to change colors there. So different metals have different thermal conductivities and are able to transfer heat more quickly or more slowly, which is exactly the same principle that allowed our aluminum plate, right? Because it's a great thermal conductor to melt that ice cube as it transferred the heat from the air up into the ice cube and then caused it to melt. The foam is actually a great insulator. And we've talked about insulators in terms of electricity, but of course, it's very, very similar, right? Instead of being a conductor, this foam is a conductive insulator. That could be good, right? Because maybe that's something we want to make our floors out of, because who likes walking on really, really hot pavement or asphalt? That can be quite painful. So that one is a much better insulator, meaning it doesn't get very, very hot or very, very cold very quickly. All right. I know I am way over time today, and it is, of course, Friday. So I know we've got lots of good weekend plans that we are excited to get started. But if you have any questions about these experiments or about Echo Live, go ahead and type them in the chat. At this time, of course, as usual, we're going to take a moment to thank the sponsors of Echo Live, like the Ford Motor Company Fund and Denso. They allow us to bring these programs to you for free every single weekday while the Michigan Science Center is closed to the public. Now, tomorrow, even though there is no episode of Echo Live, we are having another Facebook watch party for the NASA and SpaceX Crew Dragon launch. It is taking off from the Kennedy Space Center in Florida. Launch time is 3:22, but come to our Facebook page at about 2:30. We'll have a watch party going on live. And so I will be there, Paulette will be there, so that we can watch the launch all together. We can talk about all of the amazing science and engineering that went into this launch leading up. Again, that's scheduled to happen at 3:22 p.m. But if by chance, for some reason, we can't launch on Saturday because of weather or another problem, the next window is on Sunday. So if that happens, we'll be there on Sunday as well. We hope that we will see you there. Let's go ahead and see if we've got any questions. I for sure saw one in Zoom. Oh, someone asked on the candle, for our candle demonstration here, does that have anything to do with hot air balloons? And the answer is both yes and no. So we talked about how when things warm up, right? When things warm up, they expand, they start to take up more space, and therefore they are less dense than other things. So we talked about density, right? Density is how much stuff is packed into a given space. When we heat the air inside a hot air balloon, it doesn't suck air inside, but what it does is the air inside the balloon becomes less dense than all the other air down here on the surface of Earth. Things that are less dense will always rise, whereas things that are more dense will always sink. So by heating the air, by expanding those air molecules and making them less dense or less closely packed together, they become lighter than the air around us, which allows the hot air balloon to float. So awesome. Yeah, that's a great thought. That's awesome that you put that together. I am super excited. All right, let's see. Any other questions before we head out? The launch is happening in Eastern time. So Helena asked Eastern or Central time. It's happening in Eastern time. That's the same time zone here in Michigan as it is in Florida. So it's 3:22 p.m. Eastern. The Facebook watch party starts at 2:30 p.m. Eastern. If you live in a different time zone, I'm super sorry that I don't want to mess it up, so I won't say exactly what that is, but make sure you take that into account. This is a super historic event in United States history and in space travel history. You won't want to miss it. You'll want to make sure that you are able to say, I was there. I was on the Michigan Science Center's Facebook page to watch the NASA and SpaceX launch that brought the first set of NASA astronauts to the ISS on a commercial flight. It might not sound that exciting now, but once they start selling tickets to average people like you and I to go to outer space, this is going to be a super, super important day in human history. All right, let's go ahead. Let's see any last questions. I'm scrolling. Oh, lots of people feel bad for steel. Don't worry, steel is great for lots of things. Alloys are fantastic, right? And there are benefits to being a conductor versus an insulator. So don't feel bad for steel. Every metal has their purpose. So insulators are good for certain things, whereas conductors are good for others. So don't worry. The launch will be on this exact same page. So Joy asked, is the launch happening on Echo? It is still happening through our Facebook Live or through our Facebook page. So check back here if you'd like to watch it. But it is not an episode of Echo Live because we will be interacting with you through the chat, so that I won't be on video because, of course, you don't want to see me. You want to watch the rocket, right? And so you won't be able to see me, but I will be there. We'll be there to talk. Paulette will be there to answer your space questions, and it's going to be super duper fun. Steve, last question before we go. We are doing crystals next week. Lots of people asking for a show about crystals, so I've got you covered. We are going to talk about crystals next week, so make sure you're here for every episode of Echo Live so that you don't miss it, because I know you're all very, very excited about it. All right, with that, that is the end of our show today. I hope you all have a fantastic weekend. I hope I will get to interact with you tomorrow during the launch party. If not, I will get to see you again on Monday for another episode